Assignment 7.5. So this lesson was on derivatives of logarithms and integration. All right, let's do this. So let's start with derivatives first. So a bunch of practice here, 1 through 12. And let's just go one at a time and do the best we can with it. And just be a good rule follower. To take derivatives, you just follow the rule. Integration requires a little bit more thinking often. But derivatives should just be, hey, I know the rule, follow the rule, and it's done. All right. So number one, how do I take the derivative? What is the rule for a natural logarithm, ln? And the rule is, whatever's inside the logarithm, you go 1, and that becomes the denominator. So ultimately, this is how I think of it. What you see is the denominator. The derivative is your numerator. That's how I kind of want you to get at. Oops. So the derivative is the numerator. What you see is the denominator. You definitely can simplify this to just 5 over x. Let's try that again. So for the derivative, the rule is what you see is the denominator, and then the derivative of what you see is the numerator. Oops. The absolute value signs don't change what the derivative is. Oops. So again, what's in the denominator? What you see is in the denominator, the derivative is the numerator. Right? Pretty good? Number 4. I'm just writing down these 4, 5, and 6, and then I'll answer them. All right. So for number 5 or number 4 to take the derivative, first, because it's all to the exponent 4, the derivative, you multiply 4 in front and then subtract 1 to the exponent. It's important to know that 4 is not inside the logarithm in terms of y to the 4th. That 4 belongs to the ln and the y, or else you could do a property. But this is the power property for derivatives for that. And then you multiply times the derivative of what you see inside. So the derivative of ln y is 1 over y. That's it. Number 5. This one actually might be helpful to do a property first. So this 1/2 only belongs to what's inside the logarithm. It's not like parentheses around all of it. And so a property here is that 1/2 can be in front of the logarithm. That's the power property of logarithms. We're not taking the derivative. So it's not like we're subtracting 1 to the exponent. It's just 1/2 in front. They're equivalent. It's just a logarithmic property, pre-calculus. Then, when you do it, then you can do what I normally ask you. What you see is the denominator, and the derivative is your numerator, just to make it a little bit easier. For number 6, if it's a logarithm and it's not a natural logarithm, you just need a ln 5 as a hook in the denominator. So what you see, x squared subtract 1, the derivative 2x. Because the base is 5, I need an extra hook, ln 5, in the denominator, and now that completes the derivative rule. Number 7. Again, I'm just going to write them down. Oops, I wrote down number 10. I'm going to write it again. Number 7. X plus 1 times ln x. Let me just do that. So the derivative here, because we're multiplying, is the product rule, which is the first times the derivative of the second plus the second times the derivative of the first. Done. Just remember, you know your product rule. Number 8. It's going to be a little fractiony, but we'll do it. Just be a rule follower. So the rule follower in you says this is that what you see goes in the denominator, and then the derivative goes in the numerator. Well, this is the product, the quotient rule. So we need actually a fraction in the numerator to do the quotient rule. And the quotient rule is the bottom times the derivative of the top, subtract the top times the derivative of the bottom, and then the bottom squared. Kind of looks weird, right? Then, if I wanted to write it as one fraction, like times the reciprocal, you would have x minus 1, 2x minus x squared times, it's actually x subtract 1 that would be multiplying it by it. You don't need to do this, by the way. And then x squared and x subtract 1 squared. And then you could further simplify if you want to. But here, listen, I didn't really want to go down the rabbit hole. Right there. Perfect. Okay? And it's okay if we have fractions within fractions. They're complex fractions. It's equivalent. As long as it's algebraically equivalent, you get full credit. 9. F of t equals t divided by ln and the absolute value of t. All right, so the derivative here is going to be the quotient rule, which is the bottom times the derivative of the top, which is 1, subtract the top times the derivative of the bottom, which is 1 over t, and then the bottom squared. Now, I don't actually need to square it, but I will. How do I need to square it? I don't know if that's within the domain restriction. But yes, the bottom squared, and that's it. And yes, t divided by t would actually be minus 1. Number 10. Let's write it out. Let's practice it together. So the derivative of this is the chain rule. This is a derivative of a composite. So the idea is the derivative of the outside times the derivative of the inside. So the overriding ln would be this. So ln of whatever that is. So that, even though there's ln in it, that's the denominator. And then the derivative of this, ln x subtract 1, which is a fraction. So x subtract 1 is the denominator, and the derivative of x subtract 1 is 1. So you have 1 over x minus 1. That's the numerator. And then the denominator is ln x subtract 1. This is just, can you follow the rule of derivatives? And you don't have to simplify it. Number 11. Oh, an exponential, just for fun. Do you remember how to take derivatives of exponentials? So e to the exponent 3x squared, subtract 1. What's the rule for e? It's the easiest rule. You just copy it. And then the derivative of the exponent is the hook on. So the derivative of 3x squared, take away 1, is 6x. Number 12. We have another exponential. Y equals 5 to the exponent 3x squared, take away 1. The derivative of that, you copy it, and then the derivative of the exponent, and because the base is not 5, you need the extra hook on ln 5. 13, x ln x. Take the derivative there with the product rule. The first times the derivative of the second plus the second times the derivative of the first. Done. And yet simplifies to 1 plus ln x if you wanted to do that. Number 14. Use implicit differentiation here. Ln y equals x times ln 2x subtract 1. Now, the truth is, you could actually do it in two different ways here. So, if I did it implicitly, the derivative here, the derivative here is 1 over y, but it needs the hook y prime. So technically that's the numerator. And then the product rule. First times the derivative of the second plus the second times the derivative of the first, which I don't really need. And then to get y prime by itself, you just multiply everything times y. Done. Oh, what was the second way you could have done this? Is you could have taken this logarithm and write it exponentially. So to get y by itself, you could have written down y equals e to the exponent x ln 2x subtract 1. And then you could have taken the derivative of that. So you go e to that times, and then the derivative of the exponent. Oh, wait. And they are equivalent because that's what y equals. So that's what y equals. So you could actually plug that in and not even have any y's in your answer. Number 15. This one would be more challenging to get y by itself compared to the last one. So if you take the derivative, don't forget the hook. This is the product rule, the first times the derivative of the second. Now remember, what you see is the denominator. The derivative of y is y prime. That's the numerator. Plus the second times the derivative of the first. If it has a y prime in it, we need to bring it together on one side. So that's 2y times y prime subtract. Here, I'm going to write it like this. X over y. So I just put the y prime in front and I wrote it as x over y just because when you factor out a y prime, you have 2y subtract x over y is equal to ln y. So you factor out the y prime and then you divide. I don't need to simplify this. Fractions within fractions are my friends. All good. Number 16. In number 16, again, we're going to take the derivative implicitly. So the derivative of x is 1. The derivative of ln x times y. What I see is the denominator. The derivative of that is my numerator. That's the product rule. That's the first times the derivative of the second plus the second times the derivative of the first, and that's equal to 0. I'm going to separate this into two fractions so I can isolate the y prime. So we have x y prime over xy, and that subtract sign also belongs here, so that actually becomes subtract y over xy. I'm going to simplify it. So the x's divide out, the y's divide out, And then to get y prime by itself, I am going to add 1 over x and subtract 1, and then multiply by negative y. So I'll take care of that. So negative y, multiply it by that. That way the y prime is positive. Just double, double, double. Check. Got it. All right. Number 17. Can you take the second derivative here? So y equals e to the negative 3x over 3 plus 2e to the 2x, and then find the second derivative. So the first derivative, and I'll write it like this, dy by dx, that's just 1/3. So write down what you see times the derivative of the exponent. Write down what you see times the derivative of the exponent. I'm going to simplify it because I got to take the derivative again, so I'm going to make that easier on me. So negative 3 and 1/3 is just negative e to the negative 3x. 2 times 2 is 4, e to the 2x. So now I'm going to take the second derivative. I always write down the symbol for the second derivative. I write that little 2 down wrong. Let's make sure I do it right. It's 2 and then 2. I got it. Okay. I was doing it right. So there's the second derivative. So the second derivative of this is write down and then times the derivative of the exponent. Write it down times the derivative of the exponent. And there you go. And you could simplify it, but that's a great answer the way it looks. Number 18. It says let f at x equals ln root x, and sketch the graph of ln root x. On your graph, draw a tangent line at 1, 0. So we're going to sketch it, and then we're going to figure out 1, 0, and then write an equation for the tangent line that you drew. So first of all, the sketch. What's the sketch going to look like? So ln and the square root of x is actually the same as this. Can I just tell you real quick? So ln x to the 1/2, and then a property of logarithms, that 1/2 can be written in front. So in other words, it's just ln x, but it's been vertically compressed. So do you know what ln x looks like? It goes through the point 1, 0. This is the asymptote. So this is the curve, and it's just been squashed down a bit. But there's the sketch. And again, the 1/2 just makes it squash down a little bit. But that's the sketch of a logarithm. And a natural logarithm, and any log like that would go through the point 1, 0. Then it says, draw a tangent line at 1, 0. All right. And then I think it says find the equation of that tangent line. So I know it's positive, right? And so when I need an equation of a tangent line, what are the 3 things I write down? So I know x is equal to 1, y is equal to 0. For this one, I need to find the derivative. So that's why this is helpful right there. So the derivative of this is just 1/2 1 over x, right? Or 1 over 2x from here. And then plug in 1 for x, and you get 1/2, and then the equation of the tangent line is that. You don't need to go plus 0 at the end unless you really feel like it. Done. All right, number 19. We're getting there. Number 19, find equations for the tangent and normal lines. That means they're perpendicular. For that equation, so I'm going to write down y equals x squared subtract ln x plus 1 on the outside. And it gives me a point, which is nice. So that's 0, 1. So the only thing I need to find is the slope by taking the derivative. So the derivative of that is 2x. And then ln, what you see, the derivative of x plus 1 is 1. And then the derivative of 1 is 0. So it's just that. And then what number do I plug in for x is 0. So that's 0. 0 here gives me negative 1 when I simplify it. So I got negative 1. X subtract 0, or x, plus 1. That's the tangent. The normal, the reciprocal of negative 1, the opposite reciprocal would now be positive 1, and using the same point. So those are perpendicular slopes, negative 1 and positive 1. 20. Find the domain extrema points of inflection. All right, this is a good one. Y equals x subtract ln x. It's a good one when we review. It's a good one where it has a bunch of steps involved. Okay. So x subtract ln x. So first thing I want to find is the domain. Notice that x has to be a positive number for a logarithm. So the domain goes from 0 to infinity, and it doesn't include 0. The next it says find the extreme value. So I'm going to take the derivative, and then I'm going to make it equal to 0. Notice right away one of my critical numbers is 0 because it makes it undefined. And then if I add 1 over x and solve it, the other answer is 1. So the two critical numbers are 0 and 1. And recognize that 0 is not in my domain. 0 is not included. So we scratch it out, and the only critical number is 1. Then into the derivative, if I plug in like a half or a quarter or a fifth and do the reciprocal, it's actually going to be a negative answer. If I plug in a number bigger than 1, it's going to be a positive answer. So a positive 1, it creates a minimum. And if I plug 1 in here, ln 1, when 1 is inside, that answer is 0. So ln 1, that's a property. Because the base is e. E to the 0 is equal to 1. So anyways, ln 1 is 0. I'm just telling you. And we're left with 1 here. So it's 1 take away 0 or 1. So we have a minimum at 1, 1. Then I'm going to take the second derivative. So the derivative of 1 is 0. The derivative of negative 1 over x. I'm going to write it like that. So 1 over x, x to the negative 1. So negative times a negative is positive x, and subtract 1 to the exponent. So it's 1 over x squared. That's the second derivative. The only solution here is, so if I take 1 over x squared equal to 0, there is no solution to this. So that means there's no point of inflection. 1 over x squared can never equal 0. So what do I know then about the concavity? So from 0 to infinity, 1 over x squared, no matter what x value you put in, the answer is always positive. So this is all concave up with 1 minimum. So we got 1, 1. That's a minimum, right? And the entire thing is concave up. So remember, at 0, there's no value. So this is decreasing and then increasing. And you have your graph. And there's like an asymptote at 0. So it's decreasing and then increasing, and it's concave up. It really won't look like a parabola, so I didn't try to make it look like a parabola. But it's key that it's concave up, and that we have a minimum at 1, 1, and that there's a domain restriction. So it's only to the right of 0. Onward. 21. Have you seen that movie? On Disney Plus? Onward. It's a good one. 21. All right, now I'm integrating. Let's do this. All right. Looks complicated. Let's not make it complicated. If I have a monomial in the denominator, I'm going to write it as 3 fractions. So in other words, I'm going to write down 1 over e to the 2x. I'm going to write down 2e to the 2x over e to the 2x. And I'm going to write down 3e. Did I write down one of these wrong? E to the x. There it is. And this one's to the 2x. Had a feeling. So that's just x, but this one's 2x. All right. So can you write it as 3 of them? And then, once you separated it, then you can simplify it. So 1 over e to the 2x is the same as e to the negative 2x. The next one, e to the x, e to the 2x. When the bases are the same, you subtract the exponent. So x subtract 2x gives me 2e to the negative 1x. And then the last one, e to the 2x, e to the 2x, they just divide out and it's just 3. And then you integrate this. So to integrate e to the negative 2x, you would have the derivative would be negative 2, so it needs a negative 1/2 to undo it. The second one has a negative 1 for a hook, so you need a negative in front to undo it. And then the last one's just 3x. The antiderivative of 3 is 3x. Then go back and then you circle the hooks and unhook. So the negative 2 unhooks, and the rule is just copy it. The negative 1 unhook, and the answer is subtract 2e to the negative x, and then 3, and then don't forget the candy. Oops, this is 3x, and don't forget the candy. 22. Integrating, again, we're not integrating logarithms here, so we're just integrating e to the negative x. I think that's the next lesson. E to the 2x. So these are integrating exponentials from 7-2. A review. Okay. So here's another example where we could distribute as a good first step. So do some algebra. If the bases are the same and you're multiplying, you add the exponents. So that's 1x. Multiply them together, and negative x plus x, that's 0x. So actually, they eliminate, and you're just left with negative 2. And then the last one, if you go, it's 3e to the negative x dx. Then look at each one. So the derivative, the antiderivative of e to the x is e to the x. The antiderivative of negative 2 is negative 2x. So the only tricky one's the last one. And when you do the antiderivative here, you'll have a negative 1, which will make this a negative 3 e to the negative x. And then don't forget the candy. (23) We're integrating e to the 2t plus 4 squared. And then we have 2t plus 2. All right. So when I look at this, take the derivative of the, ignore the second part. Just look at this. Take the derivative of that using the chain rule. So 2 times 1 in front, subtract 1 to the exponent, and then the derivative of oops, that should be a 2. The derivative of 2t plus 4 has an extra hook on of 2. So that's kind of what it looks like. So the power rule, and then the derivative of 2t is 2. So if I put this together, it'd be 4 and then 2t plus 4. Right? All right, I want these to match up. So in order for them to match up, I'm going to factor out a 2 in front. So if I factor a 2 out, it now becomes an 8. And then I have it so I can match up. So this now matches up to this. And the only difference is I need a 1/8 in front to be able to undo the 8. Otherwise, it matches up. I can then undo this and unhook it. And the answer is 1/8. And then you copy it down. Plus the candy. All right, 24 and 25. For problems 24 and 25, let R be the region bounded by y equals e to the negative x divided by 2, and y equals 0, and x equals 0, and x equals k, where k is some positive constant. Sketch R and set up an integral for its area. All right, so how are we going to sketch this? So if I have an understanding of what y equals negative x, right, e to the x equals, then what happens when it's negative and then divided by 2? So what this does to the graph is the negative reflects it, and then all the x values are multiplied by 2. So we have a y-intercept at 1. That's going to stay the same because x is 0. It's not affected by this. But this has been reflected over and then stretched. So I just need a sketch of it, right, in terms of what's happening. So there's my sketch of what's happening, the reflection, and there's a horizontal stretch to it. And then it says x equals 0. That's there. Let me do it here. I'll change colors. So x equals 0. It says y equals 0. And then k is some positive x value. And then the area that we're talking about is here in yellow. And then the question was, can you set up integral setup, right? To find the area that I just did. So to find this, we're just integrating. Remember, not finding the volume, no pi r squared. We're just integrating. And the bounds go from 0 to k. And we just have to integrate this curve, e to the negative x over 2 dx. So there is the integral setup to find the area. And then it says find the area in terms of k. So now there's the setup. Now can you find the area in terms of k? So what's the antiderivative here? And we'll just plug in the bounds after that. So the antiderivative, the derivative of the exponent is negative a half. So to undo it, I need a negative 2 in front. So there would be a negative a half that I would undo. And then the answer would be negative 2 e to the negative x over 2. And I'm integrating from 0 to k. Then I plug in the upper bound. And our upper bound is k. So it's negative k over 2. Subtract, plug in 0, and it just gives me negative 2 or plus 2. So that's what the area would equal. for 25, these are like strong conceptual questions. These are tier 1 questions, high level. Find the volume in terms of K by revolving the region about the x-axis. So if I'm going to revolve the area and find the volume, so if I'm revolving, it's a circle, or it's a, right? So it's pi r squared. So I take that curve. That area has no gap, so it's not a washer. So it's e again to the negative 1/2 squared. So that represents the radius, the function. So there's pi r squared. And then I need to actually find the volume of that. So step 1 is I'm going to apply the 2, so it's going to multiply. So negative 1/2 times 2, this just becomes negative x. So not as bad as you thought. So the derivative of negative x is negative 1. So to undo it, I need a negative in front, so then I can unhook it. So I have negative pi. The rule is just copy it, and then I'm integrating from 0 to k. So the volume, then you plug in k first, subtract, and then you plug in 0, and you get negative pi. Or you can add pi at the end if you like. 26. I said these are high-level questions. Don't give up. Set up one or more integrals which could be used to find totally different question, 26. Bounded by f at x equals x squared. And g at x equals, I'm going to rearrange this, x cubed subtract 3x squared plus 3x. You may use a calculator to graph the equations. Well, thank you. So because I can use a calculator, let's do this. So if I'm using a calculator, let's graph both of these. So I'm just going to erase what I have to begin with. Let's go. So tab x squared is simple enough. Graph that. Tab, I can change the window after I type it in. X cubed. Move the cursor. Subtract 3x squared plus 3x. All right. So if I zoom in, here, I just want you to notice that it intersects at 3 places. So it's going to intersect up here, it's going to intersect down here, and then once again down here. So in other words, we need to set up 2 integrals to find the area that's trapped here. But I need to know where they intersect. So let's go back here, and I'm going to solve it. I think it's just as easy to solve. So we're going to go algebra and solve. And to find where they intersect, I'm going to make them equal to each other. So x squared equals, and I'm going to type in x cubed, subtract 3x squared. Got it. I got to plug this in. Let's see if I can get it done before my battery dies. So x cubed, subtract 3x squared, say go Gertz and go, plus 3x, comma x. All right, so the x values are at 0, 1, and 3. So from 0 to 1, and then 1 to 3. So I'm going to go 0 to 1, and then 1 to 3. So those are my 2 integral setups. If I go back to the graph, I just need to know which one's on top and which one's on the bottom. So for the first one, if I look real carefully, the red one is on top. And then for the second one, the blue is on top. All right. And then actually, do I have to find the area? Or just the setup? No, just the setup. Oh, wait. I don't think I need my calculator anymore. So, the first one, the g at x, and once it's defined, we can just say g at x subtract f at x. So once it's defined, you can just do that. And then the second one would be f at x subtract g at x. And there it is. So there's the integral setup to find the area. 27. I hope there's no more calculator questions because mine's dying. What? The last one? Oh, man. I like doing these. All right, I don't need a calculator. So the graph of f of x is shown at the right. I need to plug it in to approximate the integration from negative 12 to 12. So use a trapezoidal one and then use a left-hand rectangle. Let's do this. So step number one for the trapezoid. How many trapezoids? Oh, there's an equal width of 4. So the formula for a trapezoid is 1/2 times the width, which is 4. And then from negative 12 to so on, is the width is 4. So negative 12 to negative 8. So the first height is negative 10. And then I double the next height, which is 0. Remember, I'm counting by 4s, and that's the scale. The next height is 20. I double it. The next height is 30. Double it. The next height is 20 again. Double it. And the next height is 0. Double it, or just 0. And then the next height is negative 10, and it's singular. Done. So what it looks like. So the formula is 1/2 times the equal width, which is 4. And then these are the heights. No, the first height and the last height are singular. I didn't put 2 times 0 because it's 0. So all the rest are doubled in the middle. The second part, that's part A. Part B is a left-hand Riemann sum. So for a left-hand Riemann sum, it already tells you the equal width is... No, it doesn't. It tells you there are 6 rectangles. So let's do that first. So if there's 6 rectangles, to find the width, it's the top subtract the bottom divided by 6. Let me do that. So if we have 6 equal rectangles, it's the upper bound subtract the lower bound divided by 6. That's 24 divided by 6. That's still 4. But they just give it to you that way. And then we just find the left heights and plug them in. Just the left heights. So the first left height is negative 10. Then the next left height is 0. Then the next left height is 20. Then 30. Then 20. Then 0, and then I don't include the last one because it's a left one. So the last rectangle left, you don't include the last height. At the last height, you put down a 0. That's it. You did it. You did it. You did it. There's the common width. There it is, 0. It's all done, 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 done. That's called left-hand Riemann sum. Trapezoidal rule. Mr. G. Math, you did your work. I'm so proud of you. Until next time.